And let me, because there's some people who are microphone challenged, make sure that that chat is open. And this is not your class, this is your class. And let's go to that first screen. So today is October 9th. Today we're going to look more at applications, and then we're going to start defining complex numbers. Homework 1.2, which is on solving first degree equations and rational equations. Those equations where you have fractions with a variable in the denominator are due by the end of the day today. By Wednesday, the homework on literal equations and application problems, those word problems, are due by the end of the day Wednesday. And then section 1.4, which is on complex numbers, will be due next Friday. Just a reminder that there is no classes on campus on Monday, which is the 12th. Before we get started looking at more of those application problems and looking at the complex numbers, does anybody want to look at any homework problems? Anybody want to go over any questions? First question.
I thought the homework was pretty easy. I liked it.
Okay, somebody is saying that first questions in the homework, she got the right answers for X, but she can't figure out how to put it in my lab. So let's go through and look at that real quick. And the homework, which homework assignment, Val? The one that's due today or the one that was due on Wednesday? P2? Okay, great. And so the first, I'm sorry, I'm going to have to get rid of this. There we go. That's what I get for trying to have something done in advance. Sorry about this, folks. I really did think I had it open, but it was open from the previous section, and I guess it had been idle too long, so they're making me go back and redo it all. If I have them open already, they don't want to work for me. If I don't have them open, it takes too long to get back in. I'm so sorry. This is rude that you guys have to wait for me to do this. This is not your class. See if it lets me open it this time. Homework P2. And now, of course, I've closed the chat. That she had said one of the first couple of problems. Let me reopen the chat. This one just asks you to, oh Lord, not P2, 1.2. It would help if I opened the right assignment.
Sorry, Professor Torella.
Yeah?
What are we starting on, like, as soon as we're done with this part, like going through the homework, what are we going to start on? Because I had a, I wasn't.
We're going to look at more applications, more word problems, and then we're going to look at complex numbers.
Okay, thank you.
Okay. Find the value of the variable that satisfies the equation. Check your solution. Answers that are not integers may be left in fractional form or decimal form. And so over here where we've got, oh, so they're giving you an option. You can either put it in as a fraction or a decimal. So question like this, we've got 3x minus 13 equals 8. I'll add 13 to both sides, giving me 3x equals 21. And so when I divide by 3, I would just type in the x equals 7. Val, which question numbers are you wondering about? Well, you can't format it correctly. I think the other section, there were people who were asking about questions like number 11, where they're a little bit further down. You put in the answer 7 and it doesn't accept it? Did you pick choice A? You pick choice A, and then what you're going to just do is use your keyboard to type in that answer. And of course, now my keyboard has disappeared. And just type in the 7. Oh, Lord. I have no idea what happened to my toolbars at the bottom. I apologize. Yeah, just reload it and try again. I don't know what else to tell you for that one. I'm sorry. Anybody else want to look at any of the other homework questions? As I fumble with the toolbars here. There it is. Everyone all right? Okay, then last class we were looking at those word problems and we did 3 of them. I'd like to do 5 more. I have to apologize. I know that it was cumbersome working around the in the margins of the word problems, but as much as I tried, I was unable to cut and paste the questions to look at them otherwise. So if I remember correctly, we had left off with question number 16. I'd like to next look at this question number 18. Question number 18 says, including a 5% sales tax, an inn charges $252 per night. Find the inn's nightly cost before the tax is added. So I guess I'm going to ask you folks, what am I looking for? Any ideas what we need to find? Nobody? X is going to be the cost before tax. And then I'm going to write another expression. If the sales tax is 5%, it's 5% of that cost. So 5%, 0.05 of means multiply by the cost. And so then we know the total, the cost plus the tax is $252. And on the left-hand side, when I go to add, that's 1x. So adding 1x plus 0.05x gives me 1.05x equals 252. And then to solve, I'll just divide by my 1.05. And I'll get X equals, anybody want to do the division for me?
240.
240. Thank you. And so the cost is 240. The tax is 5% of 240, which would give me $12. And so when I check, the total is 252, and it checks. How is that one for everybody?
Good.
Good? All right. Next couple deal with this idea that sometimes we're asked not for one thing, but two. And because we have not yet discussed using two different variables, we're going to try to approach these problems using just a single variable. And so the next example that I'd like to look at is over here, question number 24. And question number 24 says, things did not go quite as planned. You invested $12,000, part in its stock that paid 14% interest. The rest of the money suffered a 6% loss. If the total annual income from both was $680, how much was invested at each rate? Does everybody see that we're looking for two things? We're looking for the amount in the stock and the amount in the loss. So if I let X equal the amount in the stock, we need to come up with an expression for the amount in the loss. And so anybody have an idea as to how much we would have invested in that other account if I know that I invested X in the first one? If I did some just like playing around with numbers, you know, we invested a total of $12,000. Let's say I invested $10,000 in the stocks. How much would I have invested in the other account? If the total is 12,000 and part of it was 10,000, wouldn't you subtract to find the other part, 12,000 minus 10? And so here, the amount that's in the loss would be 12,000 minus whatever X is. Now the interest in the stock is 14% times X. The other part is a loss, so we'll subtract 6% times that amount. And we know that combined we made $680. Are you folks comfortable with how I defined X, where I got the 12,000 minus X, and with where that equation came from? Are there any questions? If not, what would you do to solve this?
Distribute the 0.6 into the 12,000 and negative X.
Okay, so that gives me 0.14x minus 0.06 times 12,000 is that 7,200? Or is it 720? Help, I think it's 720.
720.
Yeah, I knew I did something wrong there. 720, and then negative times negative will give me plus 0.06x equals 680. Now, if we combine like terms, doesn't that give me 0.2x minus 720 equals 680? If we add the 720 to both sides, we get 0.2x is 1,400. And if we divide by 0.2, I get x equals 7,000. So I'm investing 7,000 in the stocks. Second part of the answer, 12,000 minus that gives me 5,000 in the other account. So far, so good.
Yep.
And now if we do a check, if I take 14% of 7,000, I get 980. If I take 6% of 5,000, I get 300. And because it's a loss, when I subtract, I do get that $680. And so it checks. That one okay for everybody? Hearing no questions. The next one I'd like to look at is number 29. 29 is one of those problems where sometimes, and I didn't put it in the suggestions for word problems, sometimes the picture's worth 1,000 words. And you'll see that if you can draw a diagram, it really helps significantly in simplifying a problem. So here we've got the rectangular painting in the picture shown measures 12 inches by 6 inches. So the picture is 12 inches by 16 inches. The frame has a uniform width around it. We know the perimeter, we know that the distance going around the outside of the frame is 72 inches. And so we want to know what's the width of the frame. And so the way the picture is drawn, does everybody see they let x equal the width of the frame? And if we know the perimeter all the way around the outside, we should be able to write an expression for the length of each side of the frame. If the picture itself is 12 inches and the width of the frame is x, how long would this entire side be? Any ideas?
You're fighting symptoms. Has to be source.
What would the length of that entire side be?
Wouldn't it be 12 plus x?
I like the 12. I like the plus. I sort of like the x, but I want to look at it. We're adding x here. Aren't we also adding another x at the bottom?
So 12 plus 2x?
I like it. And do you see how the picture kind of helps you see that we have to add the 2x? Well, x at the top and x at the bottom. And so how long would this side be?
Joker.
2 plus 2x. Sounds like somebody's having an outside conversation. Could you please mute yourself? And so that if I look at the perimeter, is everybody familiar with the idea that the perimeter is the sum of all of the sides? So I have two sides that are 12 plus 2x, and two sides that are 16 plus 2x. And so when I look for the perimeter, I add down, and so that gives me 32 plus 24 is 56 plus 8x. And we were told in the problem that the perimeter is 72. Now when we go to solve, we'll subtract 56 from each side, giving me 8x equals 16. And so dividing, we'll get that x is equal to 2. And so the final answer would be that the width of the frame is 2 inches. How is that one for everybody? Is that okay? Can I move it?
Yeah, we need more picture problems.
Okay.
That was easier.
I don't think that I picked another picture problem to do, but the next problem that I picked was question number 31. And so I'll try to do that in the margin on the other side. It says an automobile repair shop charged a customer $448, listing $63 for parts and the remainder for labor. If the cost of labor is $35 per hour, how many hours of labor did it take to repair the car? What are we looking for?
Hourly rate or hours?
We're looking for the hours. So if I let x equal the hours, what would my equation become? We know that the cost is parts and labor. The parts plus the labor is what we're charged. So the parts would be 63. If it's $35 an hour and they're working X hours, what would the expression for the labor be?
$63 plus 35x equals 448.
I like it. Is everybody comfortable with 63 plus 35x equals 448? So subtracting 63 from both sides, I get 35x equals 385. And then dividing, we get that x is 11 hours. How's that one? If that's all right, I'd like to look at one more where we have two unknowns kind of considered almost a rate problem. I'd like to look at number 70. And you know what? I'm going to be quiet for a minute and let you folks look at number 70. Can everybody read it? Suppose we agree to pay 8 cents for every problem in this chapter you solve correctly, and fine you 5 cents for every problem done incorrectly. At the end of 26 problems, we do not owe each other any money. How many problems did you solve correctly? Now be quiet for a minute and let you guys work on this one. How are you folks doing? Does anybody have an answer yet? Are we ready to go over? Is anybody there? What are you getting? Go over or not yet?
Yeah, go over. I don't know.
If you get X correct, and there are 26 problems altogether, how many did you get wrong? How would you find it? Wouldn't the number incorrect be 26 minus X? And then in terms of the money, if nobody owes anybody else money, then the money that you get, the 8 cents for each one correct, is equal to the money that you pay out, the 5 cents for each one incorrect. How does that equation look?
Okay.
So now, distributing 8x equals 5 times 26 is 130 minus 5x. We'll add the 5x, get the variables together, giving me 13x equals 130. And so dividing by 13, we get x is 10 correct. And if the 10's correct, we get 80 cents. And if there are 10 correct, then 26 minus 10 means there are 16 that are incorrect. And if we take 5 cents for each of those, that also gives us 80 cents. And so they're the same. Any better? This idea, when you know the total, in order to find two different quantities, if X is 1, then the other one will always be that difference. All right?
Okay.
Okay, so now, over the weekend when you're working on that word problem homework, if you have any questions, you can use the Help Me Solve It. You can also send me an email. Again, because it's a holiday weekend, I will be checking my email. Just not all that frequently, but I will try to make sure I check it 2 or 3 times a day. So if that's all right, then we're going to switch gears a little bit. And we're going to get into something that's called complex numbers. And when we look at complex numbers, I want to backtrack a little bit and remember some of what we did with radical expression. Does everybody remember when I took the square root of 4, positive or negative. I got 2 because 2 to the second equals 4. And I also got that other root, -2, because -2 to the second also equals 4. If I wanted to take the square root of -4, we said we'd be looking for a number that when I multiply it by itself, I get -4. And within the number systems that we've been working with, within the real numbers, was there something that I could multiply by itself and get a negative answer?
No.
No. And so we said that this did not exist. But rather than saying that it does not exist, we're going to change our phraseology here and say that it's not a real number. And if something's not real, we're going to have to start using our imaginations. And so what we're going to do is we're going to introduce a new value, I, which is going to be the imaginary unit. This will allow us to take the square roots of negative. How? What we're going to do is we're going to define I to equal the square root of -1. In which case, then, when we take I and square it, that would be taking the square root of -1 and squaring it. Remember when we had said that when we square a radical, we kind of just, because they're inverses, we just take the radicand out from underneath the radical and we get -1. And so this will allow us to take the square root of a negative number. The way in which we're going to do that is we're going to find the square root of a negative using that multiplication property of radicals. So to find the square root of a negative, by using the multiplication property of radicals. And so what's that all about, the multiplication property of radicals? Well, the multiplication property of radicals said that if I have the square root of AB, I can look at that as the square root of A times the square root of B. And we'll use this to express the root of a radical in terms of I. Of a negative radical. For example, we previously said that the square root of -4 did not exist. It's not going to be a real number But I'm going to, whenever I have a negative under the radical, I'm going to factor out the negative 1. And so now I've got the square root of 4 times negative 1. Using that square root property, that'll be the square root of 4 times the square root of negative 1. And now simplifying, the square root of 4 is 2, and the square root of negative 1 we've defined to be I. In the same way, if I wanted the square root of negative 144, because I have a negative under the radical, because I have a negative radicand, I'm going to factor out that negative 1, and I'm going to look at that as 144 times negative 1. The square root of property says, the multiplication property, pardon me, of square roots, says that's going to be the square root of 144 times the square root of negative 1, which will give me 12i.
You said
How
12 or 2?
I said 12. I didn't write 12. Thank you. And then it'll also allow us to simplify a radical expression. If I want to, for example, simplify the square root of negative 32, first I'm going to factor out the negative 1. That's the square root of 32 times negative 1. But 32 is not a perfect square. What number goes into 32 evenly, and what's the largest number that goes into 32 evenly? That is a perfect square.
Isn't it 8 and 4?
8 and 4 would work.
Oh,
But
and
we,
16 and 2.
yeah, I think 16 and 2 is better. That way we only really have to do it once. So now I'm going to take the square root of the 16, the square root of the 2, and the square root of the negative 1. The square root of 16 is 4. The square root of 2 I have to leave. And then the square root of negative 1 is I. At which point, I know my penmanship is not good, so if I were to take the square root of 4, square root of 2, and I know sometimes it's kind of hard to tell, is that I underneath the square root or behind it? And so I like to put everything that's not under the radical in front of the radical and write that as 4i radical 2. If, in my mind, that's less ambiguous. You know, it's very clear that the I is not underneath the square root, but either one of those would be acceptable. So another example, what if I have the square root of negative 125? Because it's negative, we'll take out the negative 1 first. And then how would you like to factor the 125? What's a perfect square that goes into 125 evenly?
$25 and 5.
Beautiful. So it's the square root of 25 times 5 times negative 1. And so the square root of 25 would give me 5. We have the square root of 5, which we cannot simplify. And then the square root of negative 1 is I. And so I could also write that as 5i radical 5. And so do you see how we can now take the square root of a negative number in terms of I, that imaginary unit? Quick question. Is this something that you folks are familiar with? Or is this I, this imaginary unit, the square root of a negative number, new?
No.
I've
Nope.
seen it before.
Some of you have seen it before, but some of you haven't. So I apologize to those of you who are real familiar with it, because there are some people who have never seen it before. We're going to treat it as brand new content, okay? So next thing we're going to look at then are the powers of I. Because there's an unwritten rule that we're going to never leave an exponent on I. So I'm going to generate a list of different powers of I, and hopefully we'll notice something. I to the first would just be I. If I have I to the second, well, that's the square root of negative 1 squared, which we already said is negative 1. If I have I to the third, well, can't I think of I to the third as I to the second times I, which would be negative 1 times I, which gives me negative I. And then for I to the fourth, I can think of that as I squared times I squared, which would be negative 1 times negative 1, or 1. So my first 4 powers, I have I to the first is I to the second is negative 1, I to the third is negative I, and I to the fourth is 1. Everybody with me so far?
Yeah.
Yeah.
And then what happens after that is pretty cool. If I look at I to the fifth, can I think of that as I to the fourth times I, which would just be 1 times I, or I? If I look at I to the sixth, that would be I to the fourth times I squared, which would be 1 times negative 1, or negative 1. I to the seventh would be I to the fourth times I to the third, which would be 1 times negative I, or just negative I. And I to the eighth would be I to the fourth times I to the fourth, or 1 times 1, which is 1. And you see, when I get to that, I to the fifth is I to the sixth is negative 1, I to the seventh is negative I to the eighth is 1. Do you see how all of a sudden they continue repeating? And so I could go through and generate this list, but you see how it repeats every 4. And so to find I to a higher exponent, what we need to remember are these 4, and beyond those 4, for a higher exponent, what we're going to do is we're going to divide the exponent by 4, And what's important is that we use the remainder. That word's a little bit of a blast from the past. Can anybody remember that idea of remainder when we divide? So for example, if I have I to the 35th, I'm going to take my exponent, 35, and divide it by 4. 4 into 35 would be 8. And then I have a remainder of 3. And so I to the 35th would be like I to the 3rd, which we know and love as negative I. Another example. What if I have I to the 111? No, let's make it 113. I'm going to take 113 and divide it by 4. See, 4 into 11 is twice. That would give me 8. Then I'd have 33. 4 into 33 is 8 times. And I have a remainder of 1. So I to the 113 is like I to the 1st, which is just I. And so any power of I, you should be able to rewrite without an exponent. Should we try another one?
No. I'm
No?
good if everyone.
Is everybody okay with this? When do just one more? What if I have I to the 48? What happens when you take 48 and divide it by 4?
12.
12. And is there a remainder?
No.
I'm getting a remainder of 0. And anything to the 0 power is 1. So that if your exponent is divisible by 4, it will always turn out to be equal to 1. And so we're never going to leave I with an exponent. And all of this is going to, how far down the page am I? Yeah, let me add a page. All of this is going to add to what we're going to call pure imaginary numbers. And pure imaginary numbers are numbers of the form where we have some quantity, we'll call it B, times I, where B is a real number. They're going to be the roots, the square roots, pardon me, of negative numbers. So for example, let's say I want the square root of negative 81. That would again be the square root of 81 times -1, which would give me 9i. And you see that this is a pure imaginary number. And so when we were talking about different number sets, we had the natural numbers, the whole numbers, the integers, the rational numbers, the irrational numbers. When I put the rationals and the irrationals together, I got the real numbers. And now we're going to have the real numbers, and we're going to have the imaginary numbers. If you picture that being like a Venn diagram. And when I put them together, I'm going to get the complex numbers. And so I kind of think of it like, you know, think of somebody, if you've got like real friends and then you have imaginary friends and you start mixing your imaginary friends up with your real friends, your life gets kind of complicated. And so a complex number is a number of the form a plus bi. A is the real part, and bi is the imaginary part. And what happens is, if a equals 0, we get 0 plus bi, which is just bi. So it includes the pure imaginary numbers. And likewise, if b equals 0, we'd have a plus 0 times I, which would just be a. So it's going to include all of my real numbers. The complex numbers contain all of the reals and all of the imaginaries. And so when we look at complex numbers, we have to redefine a couple of things. One thing that we want to redefine is equality. So when I look at the equality of complex numbers, I'm going to say that if a plus bi equals c plus di, then a has to equal c. The real parts are equal. And b has to equal d. The imaginary parts are equal. So for example, if I ask you to find x and y such that 3 plus xi equals y minus 2i, setting the real parts equal, I get 3 equals y. And setting the imaginary parts equal, I get x equals -2. So far, so good. If so, once we've got our complex numbers defined, we're going to start looking at operations on complex numbers. Is everybody set? Can I turn the page, or do I need to wait a minute?
Yeah, I'm good.
So then if I look at operations on complex numbers, when I add complex numbers, if I have a plus bi plus c plus di, I'm going to add the real parts, a plus c, and I'm going to add the imaginary parts. And so it's almost real, in some ways, I almost behaves like a variable, and it goes along with what you would consider combining like terms. If I were to subtract, if I had a plus bi minus c plus di, again, we're going to see that they behave very much like binomials, and we'll combine what's like getting a minus c for the real part and b minus d times I for the imaginary part.
For the imaginary part, does the I have to be outside the parentheses?
Well, b and d are going to be numbers, and so you won't have parentheses left. So for example, if I have 2 plus 7i plus 10 minus 6i, I'm going to add the real parts, or think of it almost like combining like terms. The 2 and the 10 would give me 12. And then the 7 and the negative 6 would give me negative 1. I'm sorry, no, it wouldn't. It would give me positive 1i. So that would give me 12 plus I. And so I don't necessarily have to put them in parentheses because they're going to be numbers. Does that make sense, hon?
Yeah.
So another one, let's say I have 9 plus 3i plus 2 plus 5i. When I add the real parts, 9 and 2 would give me 11. And when I add the imaginary parts, 3i and 5i would give me 8i. And you see how it's almost exactly like combining like terms. Instead, if I have 8 plus 4i minus 6 minus 2i, again, because it's subtraction, you want to think like you're distributing the negative 1. And so that would become 8 plus 4i. And distributing, wouldn't that give me minus 6 plus 2i? And so then now when I add the real parts, 8 minus 6 is 2. And 4i plus 2i is 6i. And so do you see how adding and subtracting them is very much like combining like terms? Another example, let's say I have 7 minus 2 plus 9i. This first part is a real number, but I can think of it as a complex number with 0i. So I can combine them. That would stay 7. Again, because it's subtraction, I distribute the -1. It would give me 7 minus 2 minus 9i, or 5 minus 9i. So far, so good.
Yep.
If so, let's look at a couple of other examples that are very similar, but they look a little different. What if I have 5 times the square root of -8 plus 3 times the square root of -18? What you have to remember is if there's a negative under the radical, we have to simplify and put it in terms of I first. So let's see. I think we just did quite a few of these for that square root of -8. Because it's negative, we want to take out a -1. And what perfect square goes into 8 evenly? Anybody, what goes into 8 evenly?
2 and 4.
2 and 4. So that's going to be 5 times the square root of 4 times the square root of 2 times the square root of -1, or 5 times 2 radical 2 times I, or 10 radical 2 times I. In the same way, for that -18, we'll factor out a -1, and 18 will be 9 times 2. That gives me 3 times the square root of 9 times the square root of 2 times the square root of -1, or 3 times 3 radical 2 I, or 9 radical 2 I. And now they're both pure imaginary. They both have an I, so I can add them. And they're also like radicals, so I can add them. And I get 19 radical 2 I. So let's try one more of these. Let's have you folks try one. And then let's stop here and pick up with the multiplication next class. So here, if I have the square root of -12 minus the square root of -75, simplify and tell me what you get. Is anybody else getting -3 radical 3i or -3i radical 3?
Yeah.
Yeah. Should we go over? -12 would be 4 times 3, -12, pardon, would be 4 times 3 times -1, giving me 2 radical 3i minus 75 would be 25 times -75, pardon me, would be 25 times 3 times -1, giving me 5 radical 3i. And then when I subtract 2 radical 3 minus 5 radical 3 will give me that -3 radical 3i. So those of you who have seen your imaginary numbers before, does this gel with what you know already? And those of you who have not seen them before, how's it look? Looking okay?
Yeah.
Yeah, I think it's looking all right.
All right, good. Gets a little bit more complicated when we start multiplying and dividing. So we'll leave that till next week. I'm going to stop sharing my screen. I'm going to stop recording.